Hey, thanks for taking your time to join us for this presentation. We chose to present on problem A. It is raining space dust. Our team members are Drew Britton, Zach Cheney, and Emma Cornelius. Our team number is 1047. We all go to the University of Tennessee Southern in Pulaski, Tennessee. So our problem was based around the cosmic dust particles of different sizes and different velocities. They fall to the Earth's surface from asteroids in the solar system. These particles are gathered through different means. By studying cosmic dust, the concept of matter distribution might become better understood. Our model analyzes heat generated by particles at different masses and velocities. Some assumptions that we made is that the velocity does not reach below a certain speed initially. The distance from the solar system to the Earth's surface for the particles are the same. Every particle is modeled as a sphere. The density of the atmosphere is assumed to be averaged together based on the troposphere, stratosphere, and the mesosphere initially. The particles are entering the atmosphere on a direct path perpendicular to the surface. We also assume that the hypersonic drag coefficient was equivalent to 0.9, and the Earth is a perfect sphere, and the terrain is flat all the way around.
We are modeling the particle as a sphere from when it hits the atmosphere at 85 kilometers until it reaches the surface of the Earth. Using a free body diagram and Newton's second law, we set up our differential equation. We decided that the force of drag is much more impactful than gravity. Since gravity is neglected, we had to implement a terminal velocity floor so the particles will reach the ground in finite time. When the terminal velocity is reached, dv over dt equals 0. Here we can see our parameters and ranges. When mass and area are substituted in, we gain the ability to manipulate the particle's radius and density, making it useful in determining cosmic dust composition. Additionally, here's our terminal velocity equation. After setting up our equation, excluding gravity, we solved using separation of variables. We only varied the initial condition of velocity. The initial condition for position was kept at a fixed height of 85,000 meters, corresponding to the height of the mesosphere, which contains 99.99% of the mass of the atmosphere. Calculations were based on an average atmospheric density of 0.1172 kilograms per meter cubed. Our first improved model is the same as the first except that it includes a term of variable atmospheric density. This is solved using MATLAB's ODE45 and utilizes the same terminal velocity floor of the analytical model. Scale height is typically determined experimentally. Additionally, we included the gravity directly in the differential equation and passed it to ODE45 for a solution. This model performed under the most velocity regimes. Heat accrued was calculated for each model, and at low velocities, Model 3 mirrored the analytical model, and at larger velocities mirrored Model 2.
Using each of the three models, we wrote a program in MATLAB with help with Claude Sonnet 4.5 thinking for altitude versus time and velocity versus time for the middle index initial velocity. We also plotted initial velocity versus heat for 5 different initial conditions. Here we can see the heat calculation, which is just the integral of the force of drag times velocity over the time interval of interest. For this 10 micrometer diameter particle at low velocities, we can see the third model aligns with the first, since gravity is more impactful on acceleration. Drag is likely not accurate in this low velocity range. We could see the velocity spiking in Model 3 despite entering above its terminal velocity. Since the atmosphere is static in the first model, particles rapidly lose velocity, encountering drag much earlier than they would in reality. Here we can see this particle of the same mass and density entering at 1,000 meters per second. All the graphs display the same trends across particle dimensions. The third model more accurately captures the true rate of heat accumulation, but all three captured the total heat accrued. We can see Model 2 acts as a bridge between 1 and 3 in this intermediate velocity regime. All three models are the most distinct. For the same particle entering at 10,000 meters per second, we can see both Model 2 and 3's total heat become similar, while Model 1 predicts increasingly diverging values. Two important takeaways are that higher velocity particles accumulate more heat for longer periods. These particles would be chemically altered and generate smaller particles that would fall at lower velocities. And two, lower velocity particles spend more time in the atmosphere and are more likely to be more widely distributed ultimately. Limitations, improvements, and insights. These preliminary models are based on an entry perpendicular to the surface of the atmosphere. The angle of entry could be implemented to more accurately describe atmospheric dynamics. The particles in this model are strictly spheres and constant mass. The model could be improved to consider the impact of the heat on the particle as it traverses the atmosphere. Some material would certainly be lost and chemically changed, especially for higher velocity, denser particles. Though we did incorporate a warning, Stokes drag could be implemented to more accurately capture particle behavior at lower velocities, especially in lower particle density scenarios. Additionally, the drag could be calculated on a case-by-case basis, depending on particle size and velocity profile. Parameter ranges are adequate, but could be refined depending on what strata is being analyzed. Despite being heavily simplified, the initial model still provides a decent overestimate of the heat profile at low computational cost. In conjunction with a more accurate model or real-world data, a constant could be implemented to correct for this discrepancy at greatly reduced computational cost compared to the third model. What happens to very small, low-velocity particles is not captured. Some would certainly not make it to the ground directly, being trapped in the atmosphere indefinitely. The heat associated with particles entering the atmosphere is an important consideration when estimating the distribution of cosmic dust, as it will directly influence what ultimately ends up preserved in the strata. The heat encountered is directly correlated with velocity and, by extension, mass. It is promising that the makeup of dust that fertilized prebiotic Earth over time could be estimated, potentially very accurately, based on the results of this preliminary study. Further studies would need to focus on improving the implementation of the atmospheric density calculation, analyzing the impact of heat on the particle as it descends, how the particle is chemically changed in the process, and using these results to correlate the distribution on Earth to the distribution in space. And here's our references. Thank you for your time.